Good.
Yep, we're good now. Thank you.
Okay. Well, if you feel it's beautiful, I'm honored. So on this basis, it remains a challenge to identify goals and design tasks compatible with ordinary teaching conditions. So we're talking task design here. This paper reports on a teaching experiment carried out in France with grade 12 students, that's the final year of high school in France, which led to the formulation, to some extent, by the students, of a correct formal definition of the infinite limit for sequences with minimal background logical prerequisites and in the course of a 2-hour session. On a more theoretical level, the teaching project was developed in the framework of didactic engineering, that is the theory of didactic situations, and provides opportunities to contribute to the ongoing work on its adaptation to the specific context of tertiary education. In the a priori analysis, we will highlight the didactical potential of tasks of differentiation between neighboring concepts as a pathway to advanced mathematical concepts. And in the a posteriori analysis, we focus on the nature and extent of teacher intervention in the shaping of a mathematical milieu that is conducive to the definition of an advanced mathematical concept. Okay, so this is the outline of the talk. So the first part will be a bit theoretical, but I'll skip a few slides. Maybe we can come back to them in the discussion if you like. But still, I would like to share a few theoretical inputs from maths education research, because I think some of these inputs are relevant in a general higher education context, and also some have to be borne in mind to make sense of the design choices I'll be explaining in the second part. So the bulk of the talk will be about the experiment. So I'll first explain our design choices and of course the specific design, and then report on one of the 4 controlled implementations. So a few general inputs from mathematics education research. First, the general theoretical background is the theory of didactic situations. So TDS, just as realistic mathematics education, is a constructivist framework, insofar as it relies on a theory of learning based on the tenet that new knowledge is gained when a new equilibrium is reached after a phase of destabilization of some previous knowledge. This destabilization is triggered when students engage in tasks for which their previous knowledge proves inadequate, inefficient, or inconsistent. New knowledge is to be constructed by students through their interaction with a well-designed, but I insist on it, an artificial mathematical milieu and interaction with peer students. Ideally, the milieu sends enough feedback for students to gradually adjust to it and generate a consensual, appropriate, mathematically appropriate response. This central ideal phase of the design, the interaction between students and the mathematical milieu, is said to be adidactic insofar as it should take place without direct didactical intervention of the teacher. Sorry. Well, of course, pedagogical interventions, refocusing, making everyone speak, etc., remain part of the picture. Of course, the adidactic phase is followed by a final didactic phase of institutionalization, in which the teacher is to alter the status and the wording of the response produced by the students in the first adidactic phase and make it both public and decontextualized. Of course, this approach proved fruitful for the teaching of mathematics at the primary and lower secondary levels. Sorry, it's a bit early here. So its classic studies, the TDS and didactic engineering, bear on fractions, decimals, the enlargement of 2D shapes, etc. Its adaptation to advanced mathematical teaching, however, remains challenging. So for advanced concepts, researchers working in the theory of didactic situations tend to favor co-didactic situations, also called situations with an adidactic dimension, in which the didactic teacher intervention is explicitly taken into account as an element which contributes to the shaping of the milieu. The level and nature of scaffolding or teacher guidance is regarded as a key didactic variable. Hence, the role of the teacher is of key importance. First, in a prior analysis, the role of the teacher should be explicitly taken into account, and the choices, the design choices in particular, as to didactic interventions should be justified. And in the a posteriori analysis, the actual role of the teacher in the implementation has to be studied in detail to ground the claim that the situation had some adidactic dimension, that is, that the teacher did not cross the line between scaffolding, which is allowed, and lecturing, which we try to avoid, and that students are and feel responsible for the formulation process and for its outcome. So I think I'm going to skip this one. I wanted to emphasize the fact that there's a vast literature on the teaching of limits, and it's very coherent. We have a very thorough mapping of all the difficulties, and some good ideas have been tried out, but usually teacher guidance is not taken into account. For example, in this very interesting paper of 2011, it's a very experimental situation, not at all standard teaching format. You have two gifted students working with a group of researchers for maybe 7 or even 10 1.5 hours sessions. So it's very interesting to study in detail their cognitive path. But of course, the paper bears only on what the students did, and the authors merely acknowledge in passing in the conclusion that, for instance, I intervened on multiple occasions to guide them towards the path I felt might be productive. So in this particular study, I also want to study what the teacher did actually, because it's a key variable, can't be left behind the curtain. I'll skip this one too. I'll skip that one. Still, this might be of general interest. Maybe not everyone is aware of Aline Robert's works, and I think it's really interesting. So she introduced a quite robust and easy to use classification of ways that new concepts relate to what students already know or should know already. And depending on the specific connection between old knowledge and new knowledge, different task design is involved. So to analyze the didactical challenges associated with the introduction of a new piece of mathematical knowledge, be it a concept or procedure or whatever, Aline Robert introduced a classification in 4 categories. So smooth extensions, it's my free translations from the French original, bumpy extension, answer to a problem, and formalizing, unifying and generalizing concepts. So smooth extension, you knew something before, the new item of knowledge is basically the same. For example, if you know the dot product in 2D geometry, well, you almost know all there is to know about the dot product in 3D geometry. No big deal when it comes to extending previous knowledge. Some extensions can be more bumpy. Let's say, for instance, if you talk about straight lines in 2D geometry and straight line in 3D geometry, generalization has difficulties. For instance, the definition of parallelism has to change. If you define parallelism as non-intersection in 2D geometry, well, it doesn't work in 3D geometry. And if you do analytic geometry, you need one equation to characterize a straight line in a plane, but you need 2 equations to characterize a straight line in 3D geometry, and only one of these characterizes a plane. So it's an extension, but there are difficulties in the extension, and we know they create difficulties for students. Some items of knowledge are so new that they are not extensions of things students knew before, but still, the teacher can introduce the new piece of knowledge as an answer to a problem which the students can make sense of, first condition, and students can also acknowledge the fact that the item of knowledge brought to them by the teacher does solve the problem. So, for instance, Pythagoras' theorem and its converse can be seen as an easy tool to check whether or not triangles are right-angled. Okay, students will probably not find it, but they can see that it works, and the problem to which it provides an answer makes sense to them. And finally, the most difficult probably concepts to introduce, concepts which are formalizing, unifying, and generalizing concepts. And of course, it can be argued that the limit concept in high school and even more so in tertiary education is a formalizing, unifying, and generalizing concept. And those probably cannot be introduced through a nice problem, etc., etc. Actually, fourth type of concepts is what Robert, Rogalski, and Dorier called formalizing, unifying, generalizing concepts, blah, blah, blah. So they formalize, unify, and generalize a wealth of previously encountered concepts and many others still unknown to the students. This notion was first designed for the study of challenges which are common in higher education and tertiary education in the teaching of advanced mathematical notions. So the main work designed in this context is Dorier's dissertation in the 90s on linear algebra. So there are many publications on linear algebra in the 90s, and there's a book which I recommend, published around 2000, on various strategies to introduce abstract linear algebra in the first 2 years of higher education. But we did not go for this approach in our task design on limits. So when I say we, it's because there were 3 of us involved here. So 2 high school teachers and myself. So although we acknowledge that the notion of the limit has a formalizing, unifying, and generalizing side to it, we chose a different strategy for concept introduction. The importance of the process of conceptual differentiation rests on 2 types of arguments, some of epistemological nature and some of didactical nature. So mathematicians introduce new concepts for a variety of reasons and purposes. One of the merits of the FUG approach is to remind us that not all concepts were introduced to solve new and specific problems, or to solve older problems more efficiently, or even to help ascertain statements as for proof-generated concepts. So typically, the general notion of an abstract vector space was introduced not to solve a specific problem, but in hindsight, with regard to a large share of mathematics as a body of knowledge. So concepts are also introduced to unify, generalize, simplify, and more generally, streamline parts of mathematics as a body of knowledge. On some occasions, concepts are also made explicit in a process of conceptual differentiation, not to unify, but to distinguish between 2 hitherto conflated notions. And if you study the history of mathematical analysis in the 19th century, this is quite striking that it happens on a regular basis. So this is what is written at the bottom of the slide. So these were the epistemological arguments in favor of taking into account processes of conceptual differentiation for concept introduction. Now more cognitive inputs. So from the cognitive viewpoint, explicit differentiation between neighboring concepts can lead to a reorganization of the loosely organized concept image of students. I'm assuming everyone here in the room is familiar with the distinction between concept definition and concept image. Blah, blah, blah. And to the inclusion of the concept definition as a part of the concept image. More specifically, many studies have consistently shown that students usually conflate 3 distinct mathematical properties for numerical sequences, namely, well, tending to positive infinity, not being bounded above, and being increasing or strictly increasing, at least towards the end. The main hypothesis underlying this task design, this engineering, is that students can be entrusted the task of making explicit the differences between the three properties, and that this process of differentiation can lead to the formulation of a precise formal definition of property 1, the infinite limit. Hence, in this design, the misconceptions as to property 1, that is conflating them with the other two, are not seen only as obstacles, which the designer knows have to be overcome. They're also the explicit object of students' work and stepping stones for the formulation of the target definition. That's what we tried to do. We'll see what happened. So the need felt by mathematicians on the basis of their extensive knowledge of mathematics to unify, generalize, and simplify is not something that can easily be emulated in a teaching protocol. And assuring students that a newly defined concept is very important for mathematicians and will, in years to come, be of great use in their study of mathematics may have a motivational impact, but probably doesn't help them make sense of the concept. By contrast, the need for conceptual clarification does not require an extensive view of mathematics or a premonition of future benefits, but only the ability to spot specific inconsistencies in a mathematical milieu that can be designed for that purpose. There we are. So, what's our design and what were our design choices? Just to paint the general picture here, so the institutional context. So grade 12 students, of course, majoring in mathematics and the sciences. So for the final year of high school, so in the French curriculum, it is required, but it was required, it's the formal curriculum now. We change about every 8 years. So the curriculum required that students be familiar with the intuitive notion of limits for sequences and functions. Students are expected to efficiently use some rules and method to study limits, so the algebra of limits, inequalities, squeeze theorem. So they have to be able to make use of these rules, but these are not proven. They have to admit that it's how it works and go on with your exercises. But still, students are to study mathematical definitions of limits of sequences, and the teacher in grade 12 is supposed to show them how this definition can be used to justify, prove at least a few of these theorems and rules. So we're addressing students who have some intuitive knowledge of limits, probably partly incorrect, but some intuitive knowledge of limits, and to have some experience with using the algebra of limits, etc. So it's not at all the first encounter with the word limits. We're dealing with students who have some familiarity with limits and how things work, but no proofs and no definitions so far. As far as logic is concerned, students should be familiar with quantifiers and standard logical arrows. Of course, in simple contexts, in the target definition, we will have 3 nested quantifiers. So we do not assume that students are familiar with nested quantifiers, since they have to know what the usual 2 quantifiers mean in simple contexts. So the engineering was tried out 4 times, 2 times in 2016 and twice in 2017 in a rather privileged Paris high school, but in standard teaching conditions, 2-hour sessions, and classes of about 35 students. And there were 3 of us working on this project. So the 2 teachers were co-designers of the engineering, and they're 2 experienced teachers and 2 adventurous teachers. So what are the goals of this 2-hour session? In the end, we would like to, well, first, we would like students to actually engage in a situation of definition construction, which probably was a first for them, because I know what's the situation in Australia, but it is never the case that in French middle or high school, students are involved in the formulation or the construction of a mathematical definition. So it probably was a first for students. Second goal, we would like them to gradually distinguish between three properties of sequences and become aware of their connections, tending to positive infinity, not being bounded above and being somewhat increasing somehow towards the end. And when I mean become aware of their connections, that is, if you tend to positive infinity, then you are not bounded above, but the converse does not hold. And tending to positive infinity has nothing to do with being increasing towards positive infinity. So being increasing, blah, 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 is neither a necessary nor a sufficient condition for tending to positive infinity. So we would like students to become aware of all these facts in the course of the 2-hour session. And of course, we would like to formulate a correct definition of the infinite limits. So we'd like some students to come up with them, and would like the rest of the students to acknowledge the fact that, well, they make sense and they fulfill the expectations regarding a definition of the infinite limit. So, of course, the first two definitions are rather standard. I assume it's what you guys teach. The third definition is non-standard, and I'd never seen it before, but this is what students came up with in our experiments on most occasions. And the final one is quite well known in the mathematics education literature. So this one would have been acceptable just as well. Actually, I can mention a fifth one. You can say that a sequence tends to positive infinity if and only if it's bounded below by a sequence which is strictly increasing and not bounded above. You'll do the maths. So, how did we plan to achieve these many ambitious goals? So 3 phases for the 2-hour session. So in the first phase, students are required to sort sequences according to whether or not they tend to positive infinity. So to use their intuition, their experience of limits. So collective discussion on the sorting, discussion on the issue of the uniqueness of a limit. So this is where we were expecting cognitive conflict, and collective discussion on the need for a definition. Because until then, students were taught rules and theorems about limits, but none of these were ever proven for lack of a definition. We would like students to realize that they do not have a definition for limits at some point. So in the second phase, we first ask students to write down what they think could be a definition for tending to positive infinity. So in France, sequences are used, while in the Anglo-Saxon world, they're usually X's. Don't think it makes a big difference. And then the second phase bears on the collective assessment of the candidate definitions. So of course, we do not expect students to come up with anything remotely looking like a correct definition. But in phase 2.2, we would like to entrust them the task of assessing candidate definitions and rejecting incorrect, insufficient, inadequate definitions, which is probably an unusual task for them as well, and which we think is a necessary phase before a final phase of formulation of a correct definition. So in phase 3, the teacher decides that we have to start from not bounded above and from a formal formulation of not bounded above. You will see what role it plays. Since we have been working for 1.5 hours so far, and it should have become clear to everyone that not bounded above is a necessary but not sufficient condition for tending to positive infinity. So the final task is, guys, try to strengthen this condition in order to make it necessary and sufficient. So this is how it goes. So the first phase was a phase of sorting. So you have a few sequences, and the question is, in groups of two, using whatever means you deem relevant, you can use a calculator or whatever, sort these sequences into one of these three categories. I think it tends to positive infinity. I don't know. I think it does not tend to positive infinity. So maybe you can take a few seconds to take a look at the sequences. But sequences A, B, C, and D are just here for warming up. No real challenge here. Of course, E is interesting because, of course, these are usual suspects. You all know them very well. But some students might think that E does tend to positive infinity and to negative infinity just as well. Of course, F is strictly increasing, but does not tend to positive infinity. G tends to positive infinity, but it oscillates, so it never becomes increasing. You have added small waves. H alternates between, well, that's 0 and 2n. So maybe it tends to positive infinity and to 0 just as well. I, again, waves. And J alternates between n and 3n. So it does tend to positive infinity. It's even easy to prove because it's bounded below by n. But it never becomes increasing. And the waves have a size which tends to infinity. So not only small waves, but infinitely growing waves. So a bit of a shocking situation. So it took about 20, it should take about 20 minutes for students to work on these sequences and try to sort them. So what do we expect? We would like students to acknowledge the fact that being increasing, at least from a certain rank, is neither a necessary nor a sufficient condition for a sequence to tend to positive infinity. We'd like them to realize that their current use of the word limit does not allow for a rational and consensual sorting decision for seemingly innocuous sequences such as E and H. So let me remind you what E and H are. Yeah, those which tend to positive infinity among other limits. And we would like them to say that, oh, maybe we need a definition for the word infinite limit. And coming up with definition could be a way to settle the dissensus when it comes to the sorting problem. Because as you will see, we anticipated that some students would say you tend to positive infinity only when you tend to only positive infinity. And some students would say, oh no, these tend to positive infinity and to negative infinity or to 0 just as well. So we would expect some degree of dissensus in the classroom, and this is what happened. Given what we knew of their experience and intuition and limited knowledge of limits. And so we would like to also acknowledge the fact that if we chose a definition of infinite limits, which either required or implied uniqueness, that is, if we wanted to rule out E and H as non-examples of sequences with limit positive infinity, then not bounded above would not be a sufficient condition for infinite limit. It would be if we did not require uniqueness. But okay, so if we require uniqueness, then not bounded above is a sufficient, no, is a necessary but not sufficient condition for infinite limits. Okay, so this was what we were to ideally reach at the end of phase 1. So phase 2 starts with a didactic intervention of the teacher. The teacher says, I want a definition which entails uniqueness. This is actually where some history of mathematics helps, because you may be aware of the fact that in the 19th century, mathematicians did not require uniqueness, neither for functions nor for limits. So functions could be either one-valued or multi-valued. So for instance, root 4 could be either 2 or -2. Okay? And limits did not have to be, you didn't require unicity for limits. For instance, in Cauchy, in the 1820s, in his lessons in the École Polytechnique, Cauchy writes, the limit of sine 1 over x, where x tends to positive infinity, is the whole -1 + 1 interval. So an infinity of limits, the sine 1 over x, when x tends to positive infinity. So the requirement of uniqueness is something that mathematicians gradually agreed upon at the end of the 19th century. So it's a convention, meaning it cannot emerge from the milieu. It's a decision, and you have to tell them that some other people, namely mathematicians, made this decision for them being students. So write down a definition of the infinite limit. So the role of phase 2.1 is twofold. First, to initiate a shift in tasks. So from a task of sorting sequences to a task of defining infinite limit. And also to enrich the milieu through the introduction of candidate student-generated definitions. And the bulk of phase 2, about 20 or 30 minutes, is devoted to collective work of the assessment of a selection of those candidate definitions which students came about. So the goals are to trigger an active engagement of the students in a very non-standard task, namely a defining task, or more precisely, the task of assessing and hopefully rejecting, because none of them will be correct, candidate definitions, and also to lead to a consensus within the collective comprising the students and the neutral, or rather neutral teacher on the following points. Not bounded above cannot be accepted as definitory for infinite limits, since the former is a necessary but not sufficient condition for the latter. However, it's our best guess yet, since first, it's a bona fide mathematical property, something as opposed to it becomes infinitely large or whatever, metaphors. So it's a bona fide mathematical property, something that can be defined mathematically, as opposed to metaphors such as infinitely large, globally increasing, whatever. And second, at least, it's a necessary condition, as opposed to increasing. So the final phase is, now we will start from this best shot, not bounded above, and we express it formally this way. And the task entrusted to students is, well, suggest ways to strengthen the not bounded above condition to get not only a necessary but also a sufficient condition for the infinite limit. That is, a condition which implies uniqueness, when not bounded above does not imply uniqueness for the infinite limit. Also, we chose to start from this because it has a why first perspective. I don't know if you are familiar with this distinction, which is rather classical when it comes to mathematics education research on limits. Many studies bearing on students' misunderstandings of the definition, the formal definition, or many studies such as the one I mentioned earlier by Swinyard on studies of how students gradually make sense or fail to make sense or formulate correct definitions. These studies have shown that there is a necessary reversal of viewpoints from the standard metaphors to the formal definition. Namely, the standard metaphors say something like, as n tends to positive infinity, then the values of the sequence also tend to positive infinity. So in this verbal formulation, first you have a condition on the variable, be it n or x, and then meaning either successively, temporal succession, or implication, logical implication, it's unclear, then something happens with the values of the sequence or the function. But of course, the final formal definition goes the other way around, because the overarching condition is a condition on the output values, not on the input values. So it has been spotted a long time ago that this necessary reversal of the order is a major problem for students. So starting from this definition, you start with the expected final condition. The overarching condition bears on the output values. So at least we bypass, or we hope we will bypass the problems of the reversal of viewpoints between X-first perspectives and Y-first perspectives. So what happened? So I'll skip phase one, the sorting of the sequences, but you have to take my word for it. Given what we knew of students' knowledge, intuition, and experience of limits, what we assumed would happen happened. That is, some students say, oh, tending to positive infinity means only to positive infinity. And some say, no, this one tends to positive infinity and negative infinity. That guy tends to positive infinity and zero just as well. And we make students vote and explain to one another their arguments, etc. And nothing definitive emerges. And hopefully, we would have liked them to say, oh, but maybe we need a definition to clarify this thorny issue. Well, they do not, most of the time, they do not word this in terms of we need a definition, but clearly they say, oh, we need some kind of clarification. We need a precise sorting criterion, and our intuition is at least somewhat lacking. So we ask students to take 5 minutes and write down what you think could be a definition for the infinite limit. So you get this kind of things. I'll leave it to you for 10 to 20 seconds. So of course, nothing surprising here. This is exactly the mixture of not bounded above and increasing somewhat towards the end that we were expecting. We've been teaching for a long time, and we have 40 years of mathematics education research telling us that this is going to be the case. This is the case. So you have actual students' worksheets. So what do you do with that? Well, so we ask students, so let's take the first one. What do you think of it? Do you think it's a correct definition of tending to positive infinity? So here I'm going to report on one of the 4 experiments. So in the left-hand column, you have extracts from the verbatim, so the actual exchanges among students and with the teacher in the class. So in italics are quotations, and sometimes you have, oh no, mostly quotations. And in the right-hand column, it's my analysis in terms of who does what. Is it something that the teacher does or something that the students do? And a classification of the various moves involved, because I skipped this slide in the first theoretical part. But I'm using the work of Cécile Ouvrier-Buffet, who's been working on situations of definition construction for the last 20 years. So she has classified various rational moves when it comes to defining, and I try to spot them in the classroom experiments. So this is how it started. I'm going to just show you a summary of what happened. So Victor, no, let's start here. So the teacher, so let's go, try to concentrate. So Angèle, what do you think of the first suggestion? For a sequence to tend to positive infinity, we need to have blah, blah, blah. Angèle, I think it's incorrect, since the sequence can be decreasing, then increasing. So she spots that the increasing condition is too strong. And well, so students spot that this is too strong and try to tinker with it, suggesting increasing in its last part or after some time, etc. This is an interesting move. Another episode. So are there others among you with arguments? Matthias, if we consider Fn, which one was that? Okay. So indeed, this one is increasing, but it does tend to 10,000. So Matthias, if we consider Fn, we can see that it's increasing, yet it tends to 10,000. Yes, so the sequences in our collection can be used as what? As examples, no, as counterexamples. So here, student Matthias makes a relevant use of the list of sequences from phase 1. This is what we expected. So Victor, number 2, it's written that it's increasing and not bounded above, and we said that increasing is not a factor. So here the students do not use precise or correct logical connectors. He says factor, and we were expecting something like necessary condition or sufficient condition, but okay. So usually it's up to the teacher to ask for logical reformulation when students say it's a factor, it plays a part, when students say when instead of implies, etc. So teacher again, what's the difference between these two sentences, between the first one and the second one? What differences in terms of form, so to speak? Oh, the first one's a little more vague. No, it's not vague. Everyone understood it right away. In the second one, something is added. Well, for instance, in the first one, we can say that the fact that un plus 1 is greater than or equal to un, well, it can still be bounded above, blah, 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 blah. So at least student Angèle, who is a quite able student, spots a necessary condition. So bounded above seems to be a necessary condition. Okay, so what about number 3? Let me show you what number 3 is. Again. So what about number 3? What do you make of it? Number 3 is the sequence tends to positive infinity when it is not bounded above. Looks good to me because it's a necessary and sufficient condition. So first, it is the case that this sentence states a necessary and sufficient condition. It's not very clear to me. Oh, is this the case? It's not very clear to me. This when in mathematics. Who wrote this sentence? Oh, it's you, Remy. What did you mean by when? I meant if. Blah, blah, blah. So let's write down what you meant to say. If u is not bounded above, then it tends to positive infinity. So again, you could argue that we've been through this already, but still, to bring it home to a majority of students, this has to be taken into account twice. And, well, maybe if at the end of it, most students understand that not bounded above is a necessary but not sufficient condition. Well, maybe those 5 minutes have not been wasted. And so let's write this down. What do you think, Isabel? We saw that in the case of a sequence which does this, so she does the oscillating gesture. On the one hand, it tends to positive infinity, and on the other hand, it also tends to negative infinity. That was E in the list. It wasn't bounded above, but it did have to tend to positive infinity because it wasn't bounded below either. So she spots a specific sequence which maybe tends to both positive and negative infinity. So the teacher said, we want to rule this one out. We want to find a definition such that sequence E does not tend to positive infinity. So the student's move is, so you think it needs to be bounded below to tend to positive infinity, and Isabel says, yes, that's what I mean to say. So if we take a look at the right-hand column, this is a typical move in situations of definition construction. You tinker with a candidate definition to strengthen it a tad, just to rule out an example which you want to turn into a non-example. So using imrelakatos proofs and refutations, you can call it a monster barring move. So you tinker with the definition just with an example in mind, which you want to rule out. So it's a very interesting and relevant move. So now the best they have in terms of candidate definition is not bounded above, but bounded below. We're not quite there yet. So now we've rejected all 5 candidate definitions, and all of them are incorrect. So after a quick and conceptual rejection of yet another incorrect definition, 2 students suggest a new one. So they really engage in definition construction and tinker, improve, rephrase, etc. So another pair of students has a new definition to suggest. Let's call it definition 6. Let's see what's on your worksheet. So this is what's on their worksheet. So the teacher rephrases this at, well, this is just not bounded above. So is the idea of not being bounded above an important one in order to capture tending to positive infinity? Shall we keep it? We said earlier that it's not a sufficient condition. It means we have to add another one, an extra condition. We have to make it stronger. What do you suggest? And again, students suggest, oh, it has to be bounded below as well. Okay. Ta-da. Then, an interesting move. One student also suggests to add this, un+1 greater than m, and oral emphasis on un+1 greater than m. So the teacher writes this new idea on the blackboard. So I have pictures of the blackboard, but not here. So imagine you have this sentence, and here you have un greater than m, and un+1 greater than m. This is what students suggested. Okay, there we are. So the teacher asked the class, what do you think? You can draw if it helps. You want it to prevent it from going down. Is that it? Yes, but it means that afterward, un+1 becomes un, and the next un+1 will still be greater. So this we had not anticipated, but students had been taught mathematical induction and proof by induction shortly before, and even though we hadn't thought about it, they used this knowledge of proof by induction as a resource for their tinkering with the candidate definitions for the infinite limit. So of course, this is incorrect. But what the students said is not a correct definition, but what he meant to say was what happened at rank n will happen onwards if we have n and n plus 1. So of course, the teacher does not agree. So you agree that it will not do because there's only one, well, actually two, one n and the next one. Do you guys see what Maxime is trying to do? And then Maxime, since it's written in a formal setting, now you can tinker with this syntactic expression, and the same student suggests replacing un plus 1 by un plus x. Of course, one student suggested that, and the others have a hard time making any sense of it. So the teacher asked the students to explain what he meant. And of course, this teacher also spots a problem because a new variable was introduced, but it's not quantified. So the teacher asks for quantification. Do you mean there is an x such that, or for all x in the set of natural numbers? So the student says, yeah, it has to be for any such x's. So this is what was reached in this 2016 experiment. So the teacher, okay, that's an improvement. Of course, you don't need this one, but at least it's great. We can do it better. Go ahead. I'm sure you can find it. I am. Don't you find it a little too complicated? This un plus x, can you think of a much simpler way to say this? And that year, the students suggested that final formulation, which of course is the textbook formulation. One of them. So this was a report on one of the 4 experiments. So what happened on the whole? So I'm almost done here. So the global pathway described above is in essential similar to those observed in the 3 other experiments. The list of operators and controls, that is the moves exerted by students without explicit prompts from the teacher, show an active engagement in the defining process, mostly through a usually relevant use of the lists of examples and non-examples provided by the first phase. So students manage to spot that a condition is too strong because it rules out examples, or too weak since it accommodates non-examples. Students manage to suggest ways of strengthening conditions to bar monsters and to weaken conditions when they're too strong. For instance, to replace increasing by increasing at least from a certain rank. On the other hand, other operators and controls were usually exerted by students when explicitly asked by the teacher, in particular when it came to making logical aspects explicit, so replacing rhetorical formulations such as when by implications, distinguishing between implications, converses, and equivalencies, specifying whether newly introduced variables were to be quantified universally or existentially, spotting undefined terms, and asking for reformulation clarification. No, I can skip that one. So this is the conclusion. What could be the next steps? So 2 slides with questions. So, of course, can we assess the impact of this session? Of course, in the theory of didactic situations, we go for internal verification. That is, we try to describe in detail in a priori analysis the expected cognitive path of the students, and if the data collected are consistent with the expected cognitive path, then we say our hypotheses have been validated. But of course, there are other ways to assess the impact of a teaching session, questionnaires, tests, individual interviews, whatever. But it's a challenge to design ways to specifically evaluate the impact of such a session, because we have many different expected impacts. So, for instance, you can have very general impacts. For instance, the impact on the image of mathematics as to the role of definitions in mathematics, because it was probably the first time in their education that students were involved in a defining process. So it was not only about limits, it was also about what mathematics is about and what definitions are and are for. Another group of questions is, okay, if we are fairly confident that this 2-hour session in given conditions does work quite well, should other people use it? But of course, it was designed to work in ordinary conditions. So it was not 2 students. It was not, oh, if I had 20 hours, I could do better than you can in 2 hours. Sure, but that's not real life situation. But the 2 teachers who implemented the sessions were designers of the session, which warranted their ability to work for 2 hours and not cross the threshold between scaffolding and lecturing. So they knew everything by heart, and they did it by the book. And it's a very complex 2-hour session. And if we were to popularize this task design, how could we do it? Well, I'm currently doing it, attempting to do it. But it took 1 hour for me to explain it to you. And if you had only a 1-page or 2 pages summary, maybe you wouldn't have given it twice the thought. So how to popularize such rather elaborate designs is a key question in mathematics education. And finally, does anyone care? And thank you for